There is a particular moment in human consciousness, rare and precious, yet accessible to any person willing to pause and truly contemplate their position in existence, when we pause to consider our role and placement in the cosmos, not with fear, but with genuine curiosity, not with the desire to diminish ourselves, but with an authentic hunger to understand. This moment arrives quietly, often in the still hours before dawn, or while standing beneath a starlit sky in a place where darkness still reigns, where the Milky Way stretches across the heavens in all its magnificent glory. In that moment, we become aware of a peculiar and profound truth. We are creatures capable of comprehending the universe we inhabit, even as we remain bound by the very laws that govern it. We are, in a very real sense, the universe becoming aware of itself. This capacity for self-reflection is not merely interesting, it is extraordinary. It represents something unique in the known cosmos. As far as we understand, consciousness is rare. Worlds without observers may exist in abundance, but worlds with beings capable of asking questions about their own existence are uncommon. We are privileged to exist in such a world. We are doubly privileged to possess minds capable of contemplating not just our immediate surroundings, but the entire structure of reality. Carl Sagan, that great poet-scientist of the 20th century, once wrote that we are made of star stuff. This phrase has achieved something of a cliché status in popular science writing, yet it deserves to be taken seriously. It is not mere poetry, though it reads as such. It is quite literally true. The calcium in our bones, the iron in our blood, the carbon that forms the very backbone of every molecule in our bodies, all of it was forged in the cores of dying stars and scattered across space when those stars exploded in supernovae. The oxygen we breathe, the nitrogen in our proteins, the phosphorus in our DNA, all products of stellar alchemy. We are not separate from the cosmos, but integral to it. We are its children, born from its substance, and endowed with a remarkable capacity to study our origins. This capacity for self-reflection, this ability to turn our minds back upon the very structure that created us, remains one of the most remarkable features of existence. We are the universe studying itself through the lens of conscious awareness. We are billions of years of cosmic evolution culminating in the emergence of consciousness capable of contemplating its own origins. Part 2. The comfortable universe and its discomforts. Yet for most of human history, we were unaware of just how vast our home truly is. The ancient philosophers, working from first principles and careful observation, imagined the universe as a nested series of crystalline spheres, with Earth at the center and the stars affixed to the outermost shell like jewels on a crown. This model was not arbitrary. It was based on what people observed. The night sky appeared to rotate around a fixed Earth. The sun and moon rose and set. The stars were fixed in their positions relative to one another, moving together across the sky like points on a vast, rotating shell. It was a comforting cosmology, orderly, comprehensible, and reassuringly compact. The universe, in this view, was ultimately knowable. It had an edge. It had a finite extent that human minds could, in principle, grasp. It had a purpose, to provide a home for humanity, placed by the divine at the center of creation. We occupied a meaningful place within it. Our existence mattered because we were central to the entire structure. The past 4 centuries have systematically dismantled this comfortable picture, replacing it with something far stranger and, paradoxically, more meaningful. Galileo's telescope revealed that the sun, not the Earth, held the central position in our local system. This was not a minor correction, it was a revolution. It meant that our planet, and by extension ourselves, were not central but peripheral. We orbited the sun like any other planet. Isaac Newton's mathematics showed us that the same forces governing an apple's fall from a tree also govern the dance of planets around the sun, the orbits of moons around planets, and potentially the entire cosmic structure. The universe, it seemed, operated according to mathematical principles that were identical everywhere. There was no distinction between terrestrial and celestial physics. All of reality followed the same laws. William Herschel's systematic surveys of the night sky in the late 18th century revealed that our solar system was not at the center of creation, but rather orbited within a vast disk of stars, a galaxy so enormous that the mind struggled to encompass it. This island universe, as it came to be called, contained hundreds of billions of stars, perhaps more. Our sun was not a central star but an undistinguished member of this vast collective, located partway out from the galactic center. And in the 20th century, astronomers discovered something even more humbling. Edwin Hubble, using the newly constructed 100-inch Hooker telescope at Mount Wilson Observatory, observed that many of the nebulae visible through telescopes were not clouds of gas within our galaxy, but were themselves entire galaxies, island universes similar to our own, located at distances so vast that their light had taken millions of years to reach us. This successive demolition of our cosmic importance might have produced only despair and nihilism. How could we matter if we were so small? How could our lives have meaning if we occupied such a tiny corner of an immense universe? How could anything we did or thought of significance if we were merely collections of atoms on a minor planet orbiting an ordinary star? Yet for many, the realization produced something unexpected: liberation. We are small, yes, but we are also conscious. We are able to contemplate infinity. We are the means by which the universe studies itself. And in that realization lies a profound dignity that no amount of cosmic vastness can diminish. Our significance derives not from our size or our central position in space, but from our consciousness, from our capacity to know and to understand. Part 3. The observable universe and its properties. The universe, as we know it, began approximately 13.8 billion years ago in a state of extraordinary density and temperature. We call this moment the Big Bang, though the terminology is somewhat misleading, as many physicists have noted. It was not an explosion within space, but rather the emergence of space itself, along with time, matter, and energy. From that initial, almost unimaginably hot moment, a moment so hot that the laws of physics as we understand them break down, everything we see is unfolded. In the first fraction of a second, literally a trillionth of a second or even far shorter, the universe underwent an epoch called inflation, a discovery that transformed cosmology in the 1980s. During this infinitesimal duration, the cosmos doubled in size not once, but perhaps 100 times or more in less than a trillionth of a second. This exponential expansion happened so rapidly that it stretches the mind to contemplate it. A single atom-sized region inflated to the size of the observable universe in less time than light takes to cross an atomic nucleus. This expansion stretched quantum fluctuations, the tiniest ripples in the fabric of reality itself, arising from the inherent uncertainty principle of quantum mechanics, to cosmic scales. These fluctuations would later become the seeds from which galaxies and stars grew. Without inflation, without this stretching of quantum ripples to cosmic dimensions, the universe would be nearly perfectly homogeneous and uniform. There would be no galaxies, no stars, no planets, and no observers to contemplate the cosmos. As the universe expanded and cooled, quarks combined to form protons and neutrons. These nucleons merged to create the first atomic nuclei, primarily hydrogen and helium, with trace amounts of lithium and beryllium. After about 380,000 years, The universe had cooled enough for electrons to combine with nuclei, forming the first neutral atoms in a process called recombination. This was a crucial moment in cosmic history. Light, which had been trapped in the dense, hot plasma that filled the early universe, suddenly escaped. Photons that had been constantly scattered by free electrons could now travel freely through space, unimpeded. The universe became transparent. This light, that ancient, primordial light, is still visible today, filling the entire cosmos in what we call the cosmic microwave background radiation, or CMB. It is the fossil radiation from the Big Bang, carrying with it information about the universe's state when it was only 380,000 years old. Following this first light, the universe entered what astronomers call the Dark Ages, not because it was dark in the sense of lacking light, but because it was devoid of stars. This period lasted hundreds of millions of years. During this era, the type density fluctuations stretched out by inflation continued to grow under the influence of gravity. Gas clouds collapsed, forming the first stars. These first stars were massive, burning intensely and briefly, lasting only a few million years before exploding as supernovae. These first stellar explosions were crucial for cosmic evolution. They seeded the universe with heavy elements, carbon, oxygen, iron, and all the other elements beyond helium. They released tremendous energy, heating the surrounding intergalactic gas. From the remnants of these stellar explosions, galaxies began to assemble. Subsequent generations of stars formed within these galaxies, each generation adding more heavy elements to the cosmic mix. Eventually, around a typical yellow star in a spiral galaxy we now call the Milky Way, a small rocky planet came into being about 4.6 billion years ago. Life emerged on that world relatively quickly in cosmic terms, within a few 100 million years of the planet's formation. For billions of years, life remained microscopic, single-celled organisms. Then, relatively recently in cosmic time, within the last billion years, multicellular life emerged and diversified. Consciousness eventually arose. And one day, creatures on that planet, creatures of star stuff, began looking outward and asking what lay beyond their world. This is where we find ourselves today. We are conscious beings, the products of 13.8 billion years of cosmic evolution, capable of understanding our own origins and contemplating the structure of reality. We look upward at the night sky with the same wonder that ancient humans felt, but now we have the tools of science to investigate what we see. Part 4. The vast observable universe. Today, our telescopes have allowed us to see approximately 93 billion light-years across the observable universe. This measurement requires explanation. It is not the true size of the universe itself, mind you, but rather the radius of the region from which light has had sufficient time to reach us in the 13.8 billion years since the Big Bang. The observable universe contains roughly 2 trillion galaxies, a number that was revised upward substantially in recent years as the Hubble Space Telescope and other instruments detected galaxies that were previously too distant and faint to observe. Each of these galaxies contains an average of perhaps 100 billion to 2 trillion stars. Let that sink in. 2 trillion galaxies. 100 billion to 2 trillion stars per galaxy. The numbers exceed easy comprehension. To give them context, if you were to count every star visible to the naked eye from Earth, a number that is approximately 5,000 per hemisphere on a dark night, and count one star every second without pausing for sleep, food, or rest, it would take you about 2.5 hours to finish counting all the visible stars. To count the stars in the observable universe at the same rate would require more time than has elapsed since the Big Bang itself. Even if you counted one star per nanosecond, billionth of a second, Using a computer, it would still take far longer than the age of the universe to complete the count. These numbers point to something fundamental about the cosmic structure. It is incomprehensibly vast. And yet, a crucial question haunts cosmological thinking. Why can we see only so far? The answer lies in the finite speed of light combined with the finite age of the universe. Light travels at approximately 186,000 miles per second, the universal speed limit, a constant that appears to be fundamental to the structure of reality. In 13.8 billion years, light has traveled 13.8 billion light-years through space. But due to the expansion of space itself, a phenomenon that has only accelerated in recent billions of years, driven by the mysterious dark energy, that initial light which left the edge of the observable universe when the universe was younger and much smaller has been stretched across space. The universe was much smaller in its early moments, so light from the furthest reaches has only now reached us. The edge of the observable universe lies at roughly 46.5 billion light-years away in terms of comoving distance, a measure that accounts for the stretching of space itself. This is a subtle but crucial distinction. Comoving distance measures the distance between objects, accounting for the expansion of space. If the universe were not expanding, an object 13.8 billion light-years away would be exactly 13.8 billion light-years distant. But because space has been expanding, that object is now much further away, about 46.5 billion light-years in comoving distance. The photons we receive from these distant objects have been traveling for 13.8 billion years, but their journey through expanding space has been far longer in distance than the simple product of time and light speed. Part 5. The accelerating expansion and dark energy. But here is where things become truly peculiar, where the universe reveals itself to be stranger than our intuitions would suggest. Beginning in the 1990s, a series of astronomical observations conducted by multiple teams using Type Ia supernovae as distance markers suggested something unexpected and counterintuitive about the universe's expansion. Type Ia supernovae occur when a white dwarf, the hot, dense remnant of a star like our Sun, orbits close to a companion star. Gravity pulls gas from the companion star toward the white dwarf, causing material to spiral inward. As this material accumulates on the white dwarf's surface, it becomes increasingly compressed and heated. Eventually, the entire star undergoes runaway thermonuclear fusion, exploding with a standard brightness that allows astronomers to use them as standard candles, objects whose intrinsic brightness is known, allowing us to determine their distance from their apparent brightness. These supernovae had been used to measure cosmic expansion. Cosmologists expected that the expansion of the universe should be slowing down due to gravity. All the matter in the universe attracts all other matter through gravity. This mutual gravitational attraction should act as a brake on expansion, gradually slowing the rate at which galaxies recede from one another. Yet the observations showed something completely unexpected. Rather than slowing down, the expansion appeared to be accelerating. Distant supernovae appeared dimmer than they should have been, indicating they were farther away than their recession velocities suggested. The universe was not merely expanding, it was being driven apart at an ever-increasing rate. This acceleration was attributed to something called dark energy, a mysterious form of energy that makes up approximately 68% of the universe's total energy content. By contrast, ordinary matter, the stuff of stars, planets, and our bodies, comprises only about 5% of the universe's energy content. The remaining 27% is dark matter, a substance we will discuss later. Dark energy represents one of the greatest mysteries of modern physics. We do not know what it is. We can only observe its effects. And those effects are profound and strange indeed. Whatever dark energy is, It appears to fill all of space uniformly, and it exerts a negative pressure, a kind of cosmic push that drives all matter and energy apart from one another. The universe, in other words, is not merely expanding. It is being actively pushed apart by something that fills all available space. The discovery of cosmic acceleration was so unexpected that when two different teams announced their results in 1998, many cosmologists were skeptical. Perhaps there were systematic errors in the observations. Perhaps a population of dust-ridden supernovae had been mistaken for normal ones, biasing the results. Perhaps the universe's expansion was not truly accelerating, and some other explanation could account for the observations. Yet as more observations accumulated, as different teams using different methods all found evidence for acceleration, the skepticism gradually gave way to acceptance. The universe was indeed accelerating. The expansion was indeed speeding up. And this acceleration must be driven by something, the mysterious dark energy. The nature of dark energy remains speculative. It could be the quantum vacuum energy, the lowest energy state of quantum fields, which quantum mechanics tells us is not truly zero, but has slight fluctuations and zero-point energy. The energy density of the quantum vacuum should be enormous, according to quantum field theory. Yet observations show that dark energy has a relatively small density. This discrepancy is known as the cosmological constant problem, one of the most severe problems in theoretical physics. Alternatively, dark energy could be a new kind of field, a field we have not yet discovered. It could be an exotic form of matter that we have not yet encountered. Or it could be evidence that Einstein's theory of gravity breaks down at cosmic scales, and that we need a new theory to replace it. Part 6. The anomalies in the ancient light. Yet even the strange behavior of dark energy and the accelerating expansion are not the deepest mysteries. Beyond these phenomena lie patterns in the cosmic microwave background that astronomers have puzzled over for decades. Patterns that seem difficult to explain within our standard understanding of cosmology. In 1989, NASA launched a satellite called the Cosmic Background Explorer, or COBE. Its mission was to measure the cosmic microwave background radiation with unprecedented precision. The CMB, as mentioned earlier, is the ancient light released when the universe first became transparent, nearly 14 billion years ago. It carries with it an imprint of the universe's earliest moments, information about the density fluctuations present when the universe was only 380,000 years old. What COBE found was remarkable and unexpected. The CMB was not perfectly uniform, as a naive analysis might have predicted. Instead, it displayed tiny fluctuations, variations of only 1 part in 100,000. These fluctuations were not random noise. They contained structure. They displayed patterns and correlations. They were the seeds from which all subsequent cosmic structure, galaxies, clusters of galaxies, superclusters, had grown. The discovery earned John Mather and George Smoot the Nobel Prize in Physics in 2006, recognition of the profound importance of this finding. But as more sophisticated instruments examined the CMB in greater detail, the Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, and the Planck satellite launched in 2009, something curious and puzzling emerged. The fluctuations in the CMB appeared to follow certain patterns. More curiously still, these patterns showed unexpected correlations that seemed to violate the fundamental assumption underlying all modern cosmology, that the universe should look essentially the same in all directions. This fundamental assumption is called the cosmological principle, and it is central to all modern cosmology. The principle states that, on sufficiently large scales, the universe is homogeneous and isotropic. This means it looks approximately the same everywhere, homogeneity, and from any vantage point, it appears roughly the same in all directions, isotropy. This principle is not merely assumed arbitrarily. It follows logically from our observations and from the mathematical solutions to Einstein's equations that describe a universe filled uniformly with matter and energy. Yet certain features of the CFB seem to challenge this principle in subtle but significant ways. One of the most intriguing of these anomalies involves what astronomers call the axis of evil, a phrase that has become famous in cosmological circles, though its origins were partly tongue-in-cheek. When Planck analyzed the distribution of the hot and cold spots in the CMB, scientists noticed something unexpected and difficult to explain. The universe's largest features, the quadrupole and octupole moments in the technical terminology, appeared to be aligned in a particular way. They seemed to point in a specific direction across the sky. More strangely still, this direction appeared to align with the plane of our solar system and with the direction in which we move through space relative to the cosmic microwave background. This should not be the case. If the cosmological principle is correct, if the universe is truly the same in all directions, then there should be no preferred direction. The largest structures in the CMB should be randomly oriented, distributed uniformly around the celestial sphere. The probability of them aligning with our particular cosmic motion and our solar system's plane appeared vanishingly small, odds on the order of 1 in a million. Yet they were aligned. The alignment appeared in multiple independent datasets. Different teams analyzing the data in different ways all found the same result. This alignment became known as the axis of evil, a term coined with some humor by the physicists who discovered it, referring to the notorious axis of evil from political discourse, but one that hinted at genuine puzzlement. If the largest structures in the universe happen to point toward us, toward our specific location and our specific orientation in space, what does this mean? Either the universe is not as isotropic as we believed, or we exist in a very special place, a possibility that most physicists found distasteful and counterintuitive, given the lessons of 4 centuries of diminishing human importance in the cosmos. Part 7. Multiple anomalies and the statistical challenge. But the axis of evil is not alone. There are other anomalies as well, each raising questions about the uniformity of the cosmos. The fluctuations in the CMB display a curious asymmetry. One hemisphere of the sky appears slightly hotter, on average, than the other. This dipole anomaly, technically, the dipole moment is larger than expected, could be explained if our galaxy is moving through space relative to the CMB. And indeed, our Sun does move relative to the cosmic background. The Milky Way orbits within our local group of galaxies. Our local group is drawn toward the Virgo supercluster due to its gravitational attraction. Our Sun orbits within the Milky Way. All of these motions combine to produce a net motion relative to the CMB of about 600 kilometers per second toward a point in the sky called the Great Attractor, a region toward the constellation Centaurus. However, the asymmetry in the CMB appears to be larger than our known motion alone can account for. The dipole asymmetry implies a motion of hundreds of kilometers per second faster than what we can explain from local gravitational dynamics. Some researchers have speculated that this might indicate a more fundamental asymmetry in the universe itself, not a local motion of our galaxy, but a true asymmetry in the distribution of matter and energy on cosmic scales. Furthermore, when astronomers examine the distribution of matter in galaxies throughout space, they find unexpected alignments and filamentary structures that seem to stretch across distances so vast that the universe should not have had time to communicate these distances, given its current age and the expansion of space. Some of these features appear to have coherence across scales of 1 billion light-years or more. Galaxy superclusters align in ways that seem too organized to be purely random. Filaments of galaxies stretch across the cosmos in patterns that appear to show structure and organization. How structures of such immense size came to be organized in the brief time since the Big Bang remains deeply puzzling. According to standard cosmological theory, perturbations in the density of matter grow over time due to gravity. But the growth of structure is not instantaneous. Density perturbations need time to grow to the scales we observe. The universe has not existed long enough for all the structures we observe to grow from infinitesimal perturbations to their present sizes. Then, there is the cold spot, a region of the CMB approximately 1.6 billion light-years across that appears inexplicably cold. In 2015, astronomers using data from the Planck satellite noticed that this region contained fewer galaxies than would be statistically expected. This suggested that the cold spot might not merely be an artifact of the CMB measurements, but might reflect an actual underdensity, a region of space containing genuinely less matter than average. The probability that such an underdensity would occur by pure chance appeared to be quite low, suggesting that something unusual might be happening in this region. One explanation for the cold spot involves something called a supervoid, a region of space far larger than any galaxy and containing significantly less matter than the average region. If our line of sight to distant supernovae passes through such a supervoid, the light from those supernovae would be gravitationally lensed in a way that would make them appear dimmer than expected. This effect could contribute to the apparent acceleration of cosmic expansion that we observe. Some of the apparent acceleration might be explained not by dark energy, but by the existence of underdensities in our local region of space. Part 8. The Supervoid Hypothesis and Cosmic Structure. The supervoid hypothesis gained traction as researchers continued to analyze the distribution of galaxies and the properties of the cold spot. If a genuinely massive void, a region extending perhaps 1 billion light-years across and containing perhaps 20% less matter than average, existed centered near the cold spot, it would explain several observational puzzles simultaneously. First, it would explain why the CMB appears cold in that direction. The low density of matter in a supervoid means less radiation-emitting material in that region. The photons we observe would have been scattered fewer times, and would come from a cooler region of the early universe. This would appear as a cold spot in the CMB. Second, it would explain why distant supernovae appear dimmer than expected in that direction. Light passing through a supervoid experiences gravitational lensing, a subtle bending due to the decreased curvature of space in a region of low density. This lensing would make distant objects appear slightly dimmer and slightly farther away than they actually are. Third, it would help explain the apparent acceleration of cosmic expansion. If our local region of space happens to be in an underdensity, if the matter and dark matter around us are sparser than average, then we would observe expansion that appears to be accelerating even if the universe's true expansion were not accelerating. We would simply be in a region where expansion is faster than average. But here is where matters become truly fascinating, where simple explanation gives way to deeper questions. If such an enormous supervoid exists, what explains its existence? How did such a vast region come to contain so little matter? Supervoids are expected to exist in standard cosmological models. They emerge naturally from cosmic structure formation, from the gravitational amplification of primordial density fluctuations. Yet the size and precise properties of the supervoid seemed at the edge of what random structure formation would produce. Some researchers noted that the supervoid and several other known cosmic voids were arranged in a pattern. They seemed to be positioned in a way that was not entirely random. They appeared to mark the boundaries of something. They seem to delineate a region. They form a kind of frame or structure. What if, some theorists asked, these voids were not merely random statistical fluctuations, but actual boundaries? What if they marked the edge of our local universe, the extent of the bubble of space-time that constitutes our particular cosmos within a larger multiversal structure? This question led to a radical reinterpretation of the cosmic data, a reinterpretation that began to seem less like wild speculation and more like a legitimate scientific hypothesis grounded in observational evidence. Part 9. The topology of space-time. We must now venture into more abstract territory, the realm of topology, the mathematical study of how shapes and spaces can be connected and related to one another. This is where mathematics becomes truly beautiful and strange, where the abstract and the concrete intersect. The universe, in Einstein's formulation, is not merely filled with matter and energy. Rather, matter and energy curve space-time itself. The curvature of space-time is what we experience as gravity. A massive star curves space-time dramatically, creating a funnel-like geometry around itself. A less massive object, moving through this curved space-time, follows the curve naturally, much as a marble rolled into a valley tends toward the center. But curvature is not merely a local phenomenon. The entire universe possesses overall curvature. This overall curvature, the geometry of the universe on its largest scales, can be one of three types: spherical, positively curved, like the surface of a sphere; hyperbolic, negatively curved, like the surface of a saddle; or flat, zero curvature, like an infinite plane. Current observations suggest that the universe is flat, or extremely close to flat. This means, at least approximately, that the universe has the geometry of an infinite plane, at least on the largest scales we can observe. The measurements from the CMB, from the distribution of galaxies, and from other observations all point to a flat universe. The total density of matter and energy in the universe equals the critical density, the density required for the universe to be flat. Yet this is where topology becomes relevant and crucial. A surface can be flat without being infinite. Consider the surface of a cylinder. If you measure angles and distances locally, you find that it obeys the rules of flat geometry. Yet it is not infinite. Travel far enough in one direction, around the cylinder, and you will wrap around and return to where you started. The local geometry is flat, but the global topology is non-trivial. Similarly, a torus, the surface of a donut, can have regions that obey flat geometry locally, even though globally it has a non-trivial topology. You could imagine a three-dimensional universe with flat local geometry, but with a toroidal topology. In such a universe, if you traveled far enough in one direction, you would eventually loop back to where you started. In the 1980s and 1990s, cosmologists began to explore whether our universe might have a non-trivial topology. If it did, there would be observable consequences. In a multiply-connected universe, you might see multiple images of the same distant galaxy. Light from a single source might reach us via multiple paths, having wrapped around the universe multiple times. The patterns in the CMB would be different from those expected in a simply connected, infinite universe. Such a universe would be finite, yet without boundary. It would have a finite volume, yet to those within it, moving in any direction, it would seem infinite. It would be similar to the surface of a sphere, finite yet unbounded. If you traveled far enough on the surface of a sphere, you would eventually return to where you started, but there is no boundary or edge. Part 10. Cosmic crystallography and hidden patterns. What intrigued researchers was that certain topologies would produce observable signatures in the CMB. The temperature fluctuations in the cosmic microwave background would display patterns dictated by the global topology of space. If the universe were toroidal, or had some other particular topology, the large-scale patterns in the CMB would reflect this. The mathematical structure would leave its imprint. A technique called cosmic crystallography was developed to search for such signatures. The idea is elegant. If the universe is finite and multiply connected, then there should be correlations in the CMB between regions that are separated by particular distances. These correlations would arise because the same region of the early universe appears multiple times in the observable universe at different locations due to the wraparound topology. As astronomers examined the Planck data using these techniques, they found something striking. The observed patterns in the CMB were more consistent with a finite universe possessing a non-trivial topology than with an infinite, simply connected universe. Not a positively curved, finite but unbounded universe like a sphere, which would be closed, but rather a flat, compact universe, finite in volume yet without boundary, with a non-trivial topology. Most remarkably, the size of such a universe could be estimated from the CMB data. The calculation suggested that if the observable universe exists within a compact, flat space with a particular topology, perhaps a three-dimensional toroidal topology or some other configuration, the size of that space, the characteristic length scale at which it wrapped around itself, would be only slightly larger than the observable universe itself. Perhaps 2 or 3 times larger. Perhaps as much as 5 or 6 times larger, depending on which topological model was employed. What this meant was extraordinary. The observable universe, which we perceive as vast beyond comprehension, stretching 93 billion light-years across, might be only a small portion of the true universe. The true universe might be finite, with a characteristic size of perhaps 500 billion light-years across. And we might be near its center, or we might be near its edge, or we might be somewhere in between, but in any case, the entire true universe would be defined and bounded. We would not be in an infinite universe. We would be in a pocket universe, a bubble, a finite cosmos. And if this is true, what lies beyond the boundaries of our universe? What contains it? Part 11. The Multiverse Framework. Now, if our universe is truly finite and embedded within some larger structure, what is that larger structure? The natural answer, emerging from the mathematical frameworks of modern physics, is the multiverse, a collection of many universes, potentially infinite in number, each with slightly different properties. Imagine space-time as a vast, multidimensional structure, not a simple 3 spatial dimensions and 1 temporal dimension, but something far more complex, perhaps with additional dimensions curled up at scales we cannot directly observe, as string theory suggests. Within this vast structure, universes form as bubbles, regions where space-time has slightly different properties, slightly different physical constants, slightly different histories. Most of these bubble universes would be entirely inaccessible to one another. The expansion of space itself would have separated them long before any light signal could travel between them. They would exist in complete isolation, unaware of each other's existence. Light from one universe could not reach another because the space between them is expanding faster than light travels. Yet in the mathematical framework of eternal inflation, a theory developed by Andre Linde and other cosmologists, the very process that creates universes also drives the expansion that separates them. In eternal inflation, inflation does not have a definite end. In some regions of space-time, inflation ends, and universes like ours form. But in other regions, inflation continues indefinitely, never ending, always creating new space, always spawning new bubble universes. The result is something like a cosmic foam, an infinitely large structure containing infinitely many bubbles, each potentially contain galaxies and stars and conscious beings, all unaware of the existence of their neighbors. In this framework, the multiverse is eternal and infinite. Universes have been forming forever, and new universes will form forever. There is no boundary to the multiverse and no center. It simply is infinite and eternal. Our observable universe would be one small region within one such bubble. We would perceive our bubble as the universe itself because light from beyond its boundaries could not reach us. The horizon of our universe would not be the edge of reality, but merely the edge of the region from which light has had time to reach us. We would be like creatures living in a vast theater, unaware of the larger building that contains it, unaware of the other theaters beyond our walls. Part 12. Evidence at the boundaries. Yet there is a crucial detail that makes the multiverse hypothesis testable. If the multiverse is real, and if the various bubble universes within it formed at different times and underwent different histories, then at the boundaries between bubbles, evidence of their interaction might persist. This is where the anomalies detected in the CMB become scientifically significant rather than merely curious. The cold spot, the asymmetries in the CMB, the apparent alignment of large-scale structures, all of these might be explained by the proximity of another universe. If another bubble universe lay adjacent to ours, pressed against it like two soap bubbles in a foam, then the boundary between them would show these signatures. The two universes would have slightly different properties, perhaps different dark energy densities, different temperatures in the early universe, different amounts of matter. Where they touch, we would observe anomalies. A universe with higher dark energy density would expand faster than ours. At the boundary, we might see evidence of gravitational stress, regions where the geometry of space-time is distorted. A universe with lower dark energy density would expand slower. At its boundary with ours, we might see signs of this tension. Furthermore, if multiple bubble universes surrounded us, we might expect to see multiple such signatures. And indeed, researchers examining the CMB data have suggested that evidence for not one, but several such collisions or interactions might be present in the data. Some researchers have claimed to identify up to 4 or 5 possible collision signatures arranged around us. This is what transforms the multiverse from pure speculation into a testable scientific hypothesis. We do not need to travel to other universes. We do not need to detect them directly. We need only find signatures of their existence left at the boundaries of our own universe, imprinted on the radiation from the universe's earliest moments, radiation that has been traveling toward us for nearly 14 billion years. Part 13. The fine-tuning problem and anthropic selection. To understand why the multiverse framework has become increasingly attractive to physicists, we must confront one of the deepest puzzles in cosmology, the apparent fine-tuning of physical constants and initial conditions. Our universe appears to be extraordinarily fine-tuned for the existence of life. The strength of the gravitational force, the strength of the electromagnetic force, the masses of fundamental particles, the ratio of dark energy density to matter density, all of these appear to have values that are precisely balanced, as if adjusted with extraordinary precision. If any of these constants were very much larger or smaller, the universe would be radically different. If gravity were stronger, stars would form more readily but would burn out quickly, leaving insufficient time for life to evolve. If gravity were weaker, stars would never form, and there would be no heavy elements. If the electromagnetic force were stronger, atoms would be bound too tightly together, and chemistry would be impossible. If it were weaker, atoms would not be stable. The dark energy density appears to be fine-tuned to an almost absurd degree. If dark energy density were very much higher, the expansion would have been so rapid that no galaxies could have formed. Matter would have been blown apart before it could clump together under gravity. If it were very much lower, gravity would have overwhelmed expansion, and the universe would have collapsed back in on itself billions of years ago. Yet it has a value that is approximately 10 to the power of negative 120, a decimal point followed by 120 zeros followed by a 1, of what quantum field theory predicts it should be. This is one of the greatest discrepancies between theory and observation in the history of science. If we imagine that the fundamental constants could have had any values, chosen randomly from a wide range, the probability that they would have values compatible with our existence would be incomprehensibly small. It would be like throwing a dart at the vast number line of possible values and hitting the narrow range that permits life. The probability seems impossibly low. There are several ways to respond to this fine-tuning puzzle. One is to argue that we simply got lucky. The universe happens to have the values it does, and we happen to exist to observe it. This explanation invokes the weak anthropic principle. We observe the universe to have properties compatible with our existence because we could not possibly observe a universe with incompatible properties. Another response is to invoke divine creation. A creator with infinite power and knowledge set the constants to their observed values intentionally. This removes the puzzle from the realm of science, placing it in the domain of theology or philosophy. But the multiverse framework offers a third response that is scientifically sophisticated. In a multiverse, different bubble universes would have different values of the fundamental constants, determined by the configuration of space-time in each bubble. Most universes would have dark energy densities vastly different from ours, so different that they would either collapse almost immediately or expand so rapidly that galaxies could never form. Most universes would have physical constants incompatible with chemistry, with star formation, with the existence of planets, with the emergence of life. But in the infinite multiverse, even rare combinations of physical constants would eventually occur. Universes with physical constants precisely tuned for the emergence of life would be statistically rare, but they would exist. And we, inevitably, find ourselves in one of these rare universes. We cannot observe any universe other than one with approximately our properties. From our perspective, the universe appears impossibly fine-tuned. But from the perspective of an infinite multiverse, our observation is merely a consequence of observer selection bias. This explanation, which applies not just to dark energy but to all the apparent fine-tuning of physical constants, is called the weak anthropic principle in its statistical form, or the principle of mediocrity. We should expect to find ourselves in a typical universe among those compatible with observers, not in an atypical one. Part 14. The cosmological constant problem. The fine-tuning puzzle becomes even more acute when we focus on dark energy, specifically on the cosmological constant problem that we mentioned earlier. The energy density of the quantum vacuum, the lowest energy state of quantum fields, is predicted by quantum field theory to be enormous. Quantum mechanics tells us that fields cannot have exactly zero energy, but must have quantum fluctuations, which contribute to an energy density called the vacuum energy or zero-point energy. Calculations using quantum field theory suggest that this vacuum energy should have a density of approximately 10 to the power of 113 joules per cubic meter. Yet observations of cosmic expansion show that dark energy has a density of approximately 10 to the power of -9 joules per cubic meter. These two numbers differ by a factor of 10 to the power of 122. This is the most severe discrepancy between theory and observation in the history of physics. Why is the vacuum energy so much smaller than quantum field theory predicts? No one knows. The cosmological constant problem has been called the most important unsolved problem in theoretical physics. Some physicists have proposed that quantum corrections to the vacuum energy from different fields cancel almost perfectly, leaving only a tiny residual energy. But the mechanism for this cancellation is not understood. The multiverse framework provides a possible explanation. If the cosmological constant is not determined by fundamental physics, but is instead a property of each bubble universe, determined by the configuration of space-time and fields in that bubble, then different universes would have different cosmological constant values. In most universes, the cosmological constant would have a random value determined by quantum fluctuations or by some other process. In most of these universes, the value would be so large that the universe would collapse almost immediately or expand so rapidly that galaxies could never form. But in a very rare minority of universes, the cosmological constant would happen to have a small value compatible with the existence of stars, galaxies, and observers. And we, inevitably, find ourselves in one of these rare universes. We cannot exist in any other kind of universe, so we observe ourselves in a universe with an unusually small cosmological constant. Part 15. The large-scale structure and the cosmic web. To understand how we might detect the presence of a larger containing structure, we must examine the large-scale architecture of the universe itself, the cosmic web, the filaments and voids that make up the structure of the cosmos. When astronomers map the distribution of galaxies throughout space using surveys that measure the distances to millions of galaxies, they find that it is not random. Galaxies are not scattered uniformly. Rather, they cluster. They form groups, clusters, and superclusters. Between these dense regions lie vast voids, regions containing very few galaxies. The overall structure resembles a cosmic web or foam, filaments of galaxies surrounding voids. This structure forms through a process called gravitational instability. In the early universe, as mentioned earlier, tiny quantum fluctuations were stretched to cosmic size during inflation. After inflation ended, and the universe continued to expand and cool, matter gathered preferentially in regions where the initial fluctuations had created slightly higher densities. Over billions of years, gravity amplified these tiny differences, pulling more and more matter into the overdense regions and depleting the underdense regions. Eventually, the matter in the overdense regions became so concentrated that it formed the first galaxies. These galaxies, in turn, were pulled together by gravity into groups and clusters. Superclusters form from collections of galaxy clusters, separated by vast voids containing few galaxies. The scale of this structure is impressive. The largest superclusters and voids can extend across 1 billion light-years or more. The Sloan Great Wall, a collection of galaxy clusters and filaments, stretches across more than 1 billion light-years. The Hercules supercluster, the Virgo supercluster, which contains our local group, and many others form a complex web throughout space. Yet, according to standard cosmological models, structure formation should be a continuous process. Smaller structures combine to form larger structures. There should be no preferred scale at which structure formation stops. The universe should display what is called a fractal structure, similar patterns repeating at all scales, from the sizes of galaxies to the sizes of superclusters to even larger scales. Yet when astronomers examine the distribution of structures more carefully, they find something curious. While structure does exist at scales of billions of light years, it seems to stop at certain scales. There appears to be a maximum scale to gravitationally bound structures. Beyond a certain scale, somewhere around 1 to 3 billion light-years, structures do not continue to grow or become denser. This transition has been called the end of greatness. Beyond the scale of the largest superclusters, the universe becomes increasingly homogeneous. the large-scale cosmic web gives way to an apparently smooth, uniform distribution of matter on still larger scales. This is exactly what we would expect on the basis of the cosmological principle. On sufficiently large scales, the universe is homogeneous and isotropic. Yet recent surveys of the universe's structure suggest that this transition might not be as clean as previously thought. Some large-scale structures appear to extend to scales that challenge the predictions of standard cosmology. Filaments of galaxies appear to maintain coherence across distances greater than 1 billion light-years. Alignments between distant structures suggest some form of global ordering. Part 16. The holographic principle and higher dimensions. We must now venture into territory that may seem even more exotic than what has come before, the realm of quantum information and holography. This is where string theory, quantum gravity, and information theory converge to suggest possibilities that stretch our intuition about the nature of reality. In the 1990s, theoretical physicists discovered something remarkable and counterintuitive. The properties of black holes, those cosmic regions of space-time so intensely curved that nothing can escape them, appear to contain a hidden connection to quantum information theory. When black holes emit radiation, a process discovered by Stephen Hawking in 1974, they lose mass and energy. Eventually, they evaporate completely. But this seems to violate a fundamental principle of quantum mechanics, the principle that information cannot be destroyed. This is the black hole information paradox, and it troubled physicists for decades. If a black hole contained information, a particular arrangement of matter and energy that fell into it, and then the black hole evaporated, where did that information go? It appeared to have vanished from the universe entirely, destroyed utterly. But quantum mechanics says that information can never be destroyed. In a quantum system, if you know the initial state with perfect precision, you can always, in principle, determine the final state with perfect precision, even if the system evolves through many intermediate stages. The resolution to this paradox, worked out by theorists including Leonard Susskind and Juan Maldacena, led to a profound realization: information, at a fundamental level, is not stored in the interior of a region of space. Instead, it is stored on the boundary of that region. All the information describing everything inside a volume of space can be encoded on the surface surrounding that volume. This principle is called the holographic principle. The holographic principle has profound implications for our understanding of the structure of reality. It suggests that the universe we experience, with its three spatial dimensions, might actually be a holographic projection of a lower dimensional structure. Just as a hologram can create a three-dimensional image from information encoded on a two-dimensional surface, our three-dimensional universe might be a projection of information encoded on a two-dimensional surface, the boundary of our universe. This is not merely a philosophical curiosity or a mathematical abstraction. The holographic principle has been incorporated into concrete mathematical frameworks. The most notable of these is the AD/CFT correspondence discovered by Juan Maldacena in 1997. This correspondence shows an explicit relationship between a theory of gravity in a higher dimensional space and a lower dimensional quantum field theory on its boundary. It provides a concrete realization of the holographic principle and has become one of the most important discoveries in theoretical physics. The AD/CFT correspondence suggests that a theory of gravity in a d+1 dimensional space, including the time dimension, is mathematically equivalent to a quantum field theory living on the d-dimensional boundary of that space. A three-dimensional universe with one time dimension would be equivalent to a two-dimensional quantum field theory on its boundary. A four-dimensional space, three spatial plus one time, with gravity would be equivalent to a three-dimensional theory without gravity on its boundary. This is extraordinary. It suggests that gravity is not fundamental, but is somehow emergent from a lower-dimensional quantum field theory. The curvature of space-time, which we experience as gravity, might be a consequence of quantum entanglement in a lower-dimensional system. Part 17. Embedding in higher dimensions. What does this have to do with the possibility of our universe being embedded within something larger? Everything. If the holographic principle is correct, then the universe we experience, three spatial dimensions, one time dimension, is not fundamental. It is a projection. It is information encoded on a lower dimensional surface. And that surface, in turn, might be the boundary of some higher dimensional structure. In the framework of string theory and quantum gravity, this higher dimensional structure is not some abstract mathematical concept. It is as real as the three-dimensional universe we perceive. We exist in a projection of that structure, but the structure itself is genuine. It has geometry. It has dynamics. It evolves according to physical laws. String theory suggests that the fundamental objects in nature are not particles, but one-dimensional strings. These strings vibrate in a space-time with 10 spatial dimensions, or 11 in the most advanced versions, called N-theory. But we observe only 3 spatial dimensions. What happened to the other dimensions? The answer is that the extra dimensions are curled up, compactified at scales so small that we cannot directly observe them. They form a 6-dimensional or 7-dimensional geometric structure called a Calabi-Yau manifold, compactified at scales of perhaps 10 to the power of -35 meters, the Planck scale. At our everyday scales, and even at the scales we can probe with current experiments, these extra dimensions are invisible. Yet at early times, when the universe was extraordinarily hot and dense, these extra dimensions were not compactified. They were extended and enlarged. In this early, higher dimensional phase, the universe might have had properties very different from what we observe today. Some models suggest that this extra-dimensional phase corresponds to what we call the Big Bang, not the beginning of time and space, but rather a transition from one phase of the universe to another. In this framework, our three-dimensional universe might be a three-dimensional subspace, called a brane, embedded within a higher dimensional bulk space. We live on this three-dimensional brane, unaware of the higher dimensional space around us. Four-dimensional objects or structures in the bulk space would appear to us as three-dimensional objects moving along our three-dimensional brane. If the universe is a holographic projection of a higher dimensional structure, then evidence of the underlying structure might be detectable in the universe itself. The patterns we observe, the alignments in the CMB, the structure of the cosmic web, the arrangements of voids and superclusters, might all be reflections of the underlying higher dimensional geometry. The universe would be like a shadow cast by a higher dimensional object, and the patterns of that shadow would encode information about the object itself. This provides yet another framework for understanding how our universe might show signs of being embedded within something larger, not merely as a bubble among bubbles in a multiverse, but as a holographic projection of a higher dimensional structure. The observational anomalies we detect would not be accidents or statistical fluctuations, but would be inevitable reflections of the underlying geometry. Part 18. The integrated picture. Let us now step back and consider how these various frameworks, the multiverse theory, the holographic principle, the topology of space-time, and the observational anomalies, might fit together into an integrated picture of cosmic structure. In this integrated view, our observable universe would be a finite, compact region with possibly non-trivial topology embedded within a larger universe or bubble universe. This larger universe might itself be finite or infinite, But if finite, it would be embedded within an even larger structure. And so on, potentially forming a hierarchy of ever larger containing structures. Alternatively, there might be a fundamental level at which the infinite multiverse exists, a foam of infinite bubbles, each potentially containing its own universes, each with different properties. At this fundamental level, the multiverse itself might be infinite and eternal, with no external container and no beginning or end. Yet overlaying all of this structure, at the most fundamental level, might be the holographic principle, that all of this complexity, all of these multiverses and universes and dimensions, might be a projection of information encoded on some lower dimensional surface. The three-dimensional universe we perceive, the higher dimensional bulk space of string theory, the multiverse of bubble universes, all of it might be a manifestation of information encoded on a two-dimensional or even one-dimensional surface, the boundary of some higher dimensional region. This would mean that reality has a deeply holographic nature. What we perceive as a three-dimensional universe is actually a projection of information. The curvature of space-time that we perceive as gravity is actually a manifestation of quantum entanglement in the lower dimensional encoding. The particles and fields we measure in experiments are patterns of information. But if this is true, what is the ultimate reality? Is it the information itself, encoded on the surface? Is it the geometry of the bulk space? Is it something beyond both? This is the question that theoretical physicists are grappling with as they work to develop a complete theory of quantum gravity. Part 19. Observational evidence and its interpretation. Let us now return to concrete observational data and consider how various lines of evidence might be interpreted in light of the multiverse and holographic paradigms we have discussed. First, the CMB anomalies. The axis of evil, the apparent alignment of the largest structures in the CMB with our galactic plane and our cosmic motion, becomes less paradoxical if we are not at a generic location in an infinite universe. If we are near the boundary of a finite bubble universe, or if the bubble itself has preferred directions based on its geometry, then such alignment would be expected. A location near the boundary would naturally show alignments with the boundary direction. If the universe has a toroidal topology, there would be preferred directions in space corresponding to the principal axis of the torus. A random location in an infinite universe should not show such alignments with such probability, but a location near the boundary of a finite bubble would naturally show them. Similarly, the cold spot becomes interpretable not as a mysterious anomaly, but as possible evidence of a neighboring bubble universe. If another universe, with slightly different matter density and dark energy density, pressed against ours, it would create exactly the kind of signature we observe, a region of cold CMB radiation, corresponding to a region of actual underdensity in matter. The supervoid at the cold spot's location would be exactly what one would predict from such a collision. Two universes with different matter densities would create a region of low density at their boundary, not because matter was expelled from that region, but because the region naturally accommodates less matter due to the geometry of the interface between the two universes. The asymmetry in the CMB, one hemisphere hotter than the other, could also be explained by proximity to a boundary. If our universe is not centered in its bubble, but rather off to one side, then we would observe asymmetries. The hemisphere facing toward the boundary would receive radiation differently than the hemisphere facing away. If the neighboring universe has slightly different properties, its radiation would have different characteristics. Furthermore, the distribution of the largest structures in the universe, the cosmic voids and walls, might not be random. If the universe has finite extent with particular geometric properties, the distribution of these structures would reflect that geometry. Some researchers have argued that the observed distribution of voids is more regular and pattern than random structure formation would predict. This regularity might be a signature of underlying geometry. There is also the question of cosmic variance and the apparent non-uniformity of the universe on the largest scales. In an infinite universe, we would expect to sample the cosmic distribution perfectly, with no systematic biases. Our region of space would be a representative sample of the larger whole. Yet some observations suggest we might not be in a representative location. The cold spot suggests a genuine underdensity, a deficit of matter in our cosmic neighborhood. If our universe is truly infinite and homogeneous, such large-scale deficits should be temporary, erased by the passage of time and mixing. Yet the cold spot persists. It might be that our universe is not infinite, but rather that we exist in a region of systematic underdensity created by proximity to the universe's boundary. The nature of dark energy and cosmic expansion provides another line of evidence. If our universe is embedded within a multiverse, the value of dark energy would be determined by the particular bubble universe we occupy, not by some fundamental law. Different nearby bubbles might have slightly different dark energy densities. This would create a kind of dark energy gradient in space. The gravitational fields of neighboring universes, with their different dark energy densities and matter distributions, might create subtle effects on the expansion rate of our universe, effects that might be detectable through very precise observations of cosmic expansion. Some researchers have speculated that certain anomalies in the distribution of dark energy, its apparent non-uniformity, subtle variations in its apparent density at different times and places, might be explained by such gradients created by nearby universes. Part 20. The mysteries we cannot yet solve. At this point, we must acknowledge honestly and rigorously the limits of current understanding. While the evidence for a multiverse or for our universe being embedded within something larger is intriguing and compelling to some researchers, it is not yet definitive. There are significant uncertainties, legitimate reasons for skepticism, and alternative explanations that deserve serious consideration. First, the interpretation of the CMB anomalies remains genuinely disputed among the cosmological community. Some researchers argue that the axis of evil and other anomalies are statistical fluctuations that would naturally occur in any survey of the CMB, even if the universe were truly infinite, isotropic, and infinite. The human brain is a pattern recognition machine extraordinarily adept at finding meaningful patterns in random data. Confirmation bias is a well-documented psychological phenomenon. Scientists are not immune to it. We tend to seek out data that confirms our hypotheses, and to downweight data that contradicts them. The fact that we see patterns in cosmic data does not necessarily mean those patterns have cosmological significance. They might be artifacts of our analysis methods or reflections of our expectations. However, the defenders of the multiverse interpretation correctly note that the anomalies are real. They appeared in multiple datasets analyzed by different teams using different methods. The patterns are not figments of imagination, but genuine features of the data. The question is not whether the patterns exist, but how to interpret them. Furthermore, the detection of such anomalies requires assuming a particular model of what signature we would expect to see if our universe collided with neighboring universes. If we search the data looking for signatures consistent with universe collisions, and if we do find such signatures, we have not really proven the multiverse hypothesis in the most rigorous sense. We have only confirmed that patterns consistent with that hypothesis exist in the data. This is weaker evidence than finding something we explicitly predicted that would be very unlikely under alternative hypotheses. There is also the question of selection bias and analysis and publication. Researchers interested in multiverse hypotheses will naturally invest more effort in analyzing the data for multiverse signatures than researchers skeptical of the multiverse. This could create a publication bias toward papers finding evidence for the multiverse and against papers failing to find such evidence. Over time, this bias could skew the scientific literature toward a multiverse interpretation even if the true answer remains uncertain. Moreover, many of the predictions of multiverse theory remain untestable in principle. We cannot directly observe other universes. We cannot measure the properties of higher dimensional spaces. We cannot travel to the boundaries of our universe and verify what lies beyond. Much of the theoretical framework of string theory, eternal inflation, and the cosmic landscape remains unverified and may be fundamentally untestable with technologies we can realistically imagine. Some eminent physicists have argued that the multiverse idea, despite its mathematical appeal and elegance, represents a retreat from the traditional goals of physics. Science aims to explain observations with a minimum number of assumptions and entities. The multiverse assumes an infinite number of unobservable universes to explain the apparent fine-tuning of one observable universe. This seems, to some critics, like a kind of intellectual capitulation, adding infinities to mathematics to avoid confronting deep unsolved problems. If the universe appears fine-tuned, the skeptics argue, that suggests we are missing something fundamental, some principle we have not yet discovered that explains the fine-tuning. Invoking an infinite multiverse seems like giving up the search for that principle. Yet others counter that this criticism misses the point. The multiverse is not invented arbitrarily. It emerges naturally from taking seriously the mathematics of quantum mechanics, inflation, and string theory. If the mathematics points toward the multiverse, then we should follow the mathematics, even if it leads us to conclusions we find uncomfortable or philosophically unsatisfying. Our aesthetic preferences about what physics should say are less important than finding truth. The honest truth is this: we do not yet know whether our universe is truly embedded within a larger multiverse, or whether it is all that exists. The evidence is suggestive, but not conclusive. The theoretical frameworks are mathematically elegant and internally consistent, but largely untestable. Future observations might clarify the picture, providing definitive evidence for or against the multiverse. Or we might find that the anomalies disappear under more careful analysis, and the universe returns to the traditional picture of a single, infinite cosmos. Part 21. The future of observational cosmology. Yet the search for answers goes on, and with each passing year, our instruments grow more precise and our understanding deepens. Multiple observational programs are underway that may eventually help clarify these fundamental questions. The James Webb Space Telescope, launched in 2021 and now beginning its observations, will allow unprecedented examination of the universe's most distant and earliest galaxies. By observing galaxies that existed within the first few 100 million years after the Big Bang, JWST can test predictions about how structures should have formed in the early universe. If the universe is embedded within a larger structure, we would expect certain patterns of structure formation to be suppressed, while others are enhanced. The geometry of a finite universe would impose constraints on the density fluctuations that could exist, constraints that would leave signatures in the observed distribution of early galaxies. JWST's infrared observations will also allow measurement of the cosmic microwave background to even higher precision than previously possible, as it can detect the CMB imprint on distant galaxies. This will refine our measurements of the CMB power spectrum, potentially revealing additional details about the universe's topology and geometry. New ground-based observatories are also coming online. The Vera Rubin Observatory, currently under construction in Chile, will systematically survey billions of galaxies and will detect trends and phenomena such as supernovae with unprecedented frequency. This flood of data will allow for statistical tests of multiverse predictions with far greater precision than currently possible. The observing time available at Vera Rubin will allow astronomers to measure the distances and properties of millions of galaxies with high precision. This will enable detailed mapping of the large-scale cosmic structure, revealing whether the distribution of voids and superclusters displays the patterns expected if we are embedded within a larger structure. Furthermore, gravitational wave detectors such as LIGO and Virgo have opened an entirely new window on the universe. Gravitational waves are disturbances in space-time itself, produced by colliding black holes and neutron stars, but potentially also by the collision or interaction of universes in the multiverse framework. As more gravitational wave events are detected and analyzed, patterns may emerge that either support or contradict multiverse predictions. If universes genuinely interact or collide, they should produce gravitational wave signatures. The frequency and characteristics of detected gravitational waves might reveal evidence of such interactions. Perhaps most promisingly, future observations of the cosmic microwave background with even higher sensitivity and angular resolution than current satellites might reveal new details about its structure. Several proposed space missions would measure the CMB to sensitivities many times better than Planck. With such data, the statistical significance of anomalies such as the axis of evil could be definitively established. New anomalies might be discovered that provide additional evidence for or against the multiverse hypothesis. Part 22. Theoretical developments and new frameworks. While observational work continues, theoretical physicists are also making progress on several fronts. String theorists are refining their understanding of the cosmic landscape, working to understand how the enormous number of possible string theory vacuum states, the different topologies and configurations that spacetime could adopt, relate to the properties of different bubble universes. Cosmologists are developing new mathematical techniques for analyzing large-scale structure and searching for subtle signatures of extra-dimensional effects. Quantum gravity researchers are working to develop testable predictions from the holographic principle, predictions that might eventually be confirmed or refuted by observations. Some theorists are exploring the possibility that the apparent fine-tuning of physical constants might be explained not by the multiverse, but by a new principle of symmetry or conservation law that we have not yet discovered. Others are working on modifications to gravity that might eliminate the need for dark energy, potentially simplifying the cosmological picture. There is also ongoing work on the interpretation of quantum mechanics itself. Different interpretations of quantum mechanics have different implications for the nature of the multiverse. The many worlds interpretation, for example, suggests that all possible outcomes of quantum processes actually occur, creating a vast branching structure of parallel universes. This is different from the multiverse of bubble universes and eternal inflation, but the two concepts might ultimately be connected. As theoretical and observational work continues, a gradually clearer picture of cosmic structure may emerge. It may reveal a cosmos far more complex and vast than our ancestors imagined, a cosmos in which our universe is merely one small bubble among infinitely many, each with different properties and histories. Part 23. The philosophical and spiritual implications. Regardless of whether the universe proves to be embedded within a larger structure or stands alone as the sole cosmos, the act of asking these questions and exploring these possibilities has profound philosophical significance. For most of human history, we believed ourselves central to creation. The earth was the immobile center of the cosmos, and the heavens revolved around us. This was not mere superstition, but emerged from our direct sensory experience and our apparent lack of motion relative to the stars. It took centuries of careful observation and revolutionary thinking to overturn this assumption and recognize that we orbit the sun, not the reverse. Then, as telescopes revealed the vastness of space and the insignificance of our planet within that vastness, we faced a spiritual crisis of considerable magnitude. How could we matter if we were so small? How could our lives have meaning if we occupied such a tiny quarter of an immense universe? How could our thoughts, feelings, and aspirations have significance if they were nothing but fleeting patterns of matter in an indifferent cosmos? The answer that emerged was not a comfortable one, but it was liberating and ultimately ennobling. Our significance does not derive from our size or our central position. It derives from our consciousness, from our capacity for understanding, from our ability to contemplate infinity, and to ask profound questions about the nature of existence. We are creatures capable of understanding our place, of studying the universe we inhabit, of asking profound questions about existence itself. The universe's vastness did not diminish our importance. In some sense, it magnified it. We are the means by which the universe understands itself. Now we face the possibility that even our universe is not unique, not final, not the ultimate level of reality. If confirmed, this would once again require us to revise our understanding of our place in the cosmos. Yet, as before, there is cause for wonder rather than despair. If we are living within a structure vastly larger than we currently comprehend, that larger structure itself would exemplify the same principles that govern our visible cosmos. It would follow the same laws of physics, be governed by the same mathematics, operate according to the same principles of quantum mechanics and general relativity. Our universe, as strange and vast as it is, would be part of something even stranger, even more vast. Moreover, the fact that we can even conceive of such possibilities, that we can develop mathematical theories predicting the existence of structures beyond our universe, that we can search observational data for signatures of hidden realms, that we can contemplate our own embeddedness within greater wholes, this capacity represents something remarkable. It is evidence of the human mind's extraordinary reach, its ability to extend thought and imagination far beyond the limitations of immediate sense experience. We are creatures of matter, forged in stellar furnaces, governed by the laws of physics, and yet capable of understanding those very laws. This capacity for understanding, this drive to know, is perhaps the most fundamental truth about what it means to be human. Part 24. The beauty of mathematical reality. As we contemplate these vast structures and complex theories, we must spend time appreciating the extraordinary fact that we can contemplate them in all, that mathematics allows us to reason about universes we cannot see and spaces we cannot directly perceive. Mathematics is one of humanity's greatest achievements. It is a language for describing patterns and relationships with perfect precision. It is remarkable that the universe appears to be fundamentally mathematical, that the deepest laws of physics can be written as equations, that the behavior of reality follows mathematical rules with exquisite precision. The fact that we can write equations describing curved space-time, that we can use tensor calculus to describe the structure of the universe, that we can employ complex analysis and differential geometry to understand quantum fields, this is extraordinary. It suggests that mathematics is not merely a tool we invented to describe nature, but that nature itself is fundamentally mathematical. This raises profound philosophical questions. Is mathematics discovered or invented? When Einstein developed his field equations of general relativity, did he discover fundamental truths about reality that existed eternally in some platonic realm, waiting to be found? Or did he invent a mathematical structure that happened to describe reality accurately? The question may be ultimately unanswerable, but the distinction matters philosophically. If mathematics is discovered, then it implies that mathematical truths exist independent of us, that the equations of general relativity existed in some abstract realm before Einstein was born, and that his genius consisted in perceiving those pre-existing truths. If mathematics is invented, then we created the language of mathematics, and its effectiveness in describing reality is a remarkable coincidence, or perhaps a selection effect. We invented mathematics to describe reality, so naturally it works well for that purpose. We might have invented a different mathematical language that worked equally well. But either way, the fact that we can use mathematics to reason about the structure of the universe, to contemplate multiverses, to imagine higher dimensional spaces, to predict the properties of particles before we can observe them, testifies to something profound about the nature of reality and about human cognition. Eugene Wigner, the renowned physicist and philosopher, famously wrote of the unreasonable effectiveness of mathematics in the natural sciences. He was struck by the fact that abstract mathematical structures, developed with no particular application in mind, often proved to describe natural phenomena with astonishing precision. The complex numbers, invented by mathematicians exploring abstract algebraic structures, turn out to be essential for describing quantum mechanics. Non-Euclidean geometries, developed as pure mathematics without any application to physics, turn out to describe the structure of curved space-time. Symmetry groups studied by pure mathematicians turn out to govern the interactions of fundamental particles. This unreasonable effectiveness suggests that there is something deep about the mathematical structure of reality. The universe, in some sense, is mathematical. The laws it follows are mathematical laws. The patterns it displays are mathematical patterns. And we, creatures of the universe, are capable of understanding these patterns because we too are part of the universe, made of the same star stuff, governed by the same laws. Part 25. The Eternal Quest and Final Reflections. We come at last to the conclusion of this exploration, though in a real sense there is no conclusion. The quest to understand the structure of reality is eternal, open-ended, and never complete. Each generation of scientists, equipped with more precise instruments and deeper theoretical insights, advances our knowledge. And yet the horizon of the unknown recedes forever into the distance, always calling us to look further, to understand more, to contemplate ever deeper mysteries. The question of whether our universe is embedded within something larger represents one of the great frontiers of contemporary cosmology. It is a question that emerges from careful observation of the cosmos and from rigorous application of mathematical principles. It is a question that has no easy answer. Yet the very fact that we can ask it, and that we can develop frameworks to investigate it, is testament to the remarkable capabilities of human intelligence and the power of the scientific method. Perhaps, in the coming decades, new observations will definitively answer this question. Perhaps we will discover that the anomalies in the cosmic microwave background are indeed signatures of neighboring universes. Perhaps we will detect gravitational waves or other phenomena that reveal the structure of a larger multiversal space. Perhaps astronomers will find that the largest structures in the universe display patterns indicating an underlying geometry extending beyond our observable universe. Or perhaps, as new data accumulates and as our theories evolve, the anomalies will be explained by mechanisms we have not yet imagined. Perhaps the universe will prove to be infinite, and ultimately self-contained, a single vast cosmos with no external structure surrounding it. Perhaps some new principle of physics, yet to be discovered, will resolve the fine-tuning problem and eliminate the need for the multiverse hypothesis. Either way, the journey of discovery continues. The universe, and the larger structure it may be embedded within, will gradually yield its secrets to patient investigation and bold imagination. The process is slow, methodical, careful, but it is also relentless, driven by human curiosity and the desire to understand. What matters is that we continue to ask questions, that we continue to observe the cosmos with ever more sensitive instruments, that we continue to theorize about its structure, testing our theories against observations, that we maintain the humility to acknowledge the limits of our understanding, while maintaining the audacity to push against those limits, that we preserve the sense of wonder that has animated human inquiry since we first looked up at the night sky and asked what we were seeing. We are the universe studying itself. We are made of star stuff, contemplating the stars. We are conscious creatures in a cosmos we have only begun to understand, capable of asking profound questions about the deepest nature of reality. This is not insignificant. This is perhaps the most important thing in existence. If the universe is indeed inside something much bigger, then we are even tinier than we thought, even more improbable, even more insignificant by measure of physical size. Yet, paradoxically, our ability to comprehend even a fraction of the truth about reality becomes all the more remarkable. We are not diminished by our smallness, but elevated by our knowledge. We are billions of years of cosmic evolution culminating in consciousness capable of contemplating infinity. The numbers are staggering. 1 trillion galaxies. 100 billion to 2 trillion stars per galaxy. A universe stretching 93 billion light-years across, yet potentially being merely a bubble within something vastly larger, containing infinitely many other bubble universes, each with different properties, each potentially containing countless stars and planets and observers. The numbers strain comprehension to their limits. They push the boundaries of human imagination and our ability to think in abstract terms. Yet we comprehend them. We build theories about them. We search for evidence of structures beyond our universe. We are conscious, creative, curious creatures, born from the universe itself, capable of understanding its structure. This capacity for understanding, this drive to know, is perhaps the most fundamental truth about what it means to be human. We are not passive observers of the universe. We are active participants in its ongoing self-discovery. Through our investigations, through our theorizing and observing, the universe becomes aware of itself. As we continue to investigate the cosmos, as we develop more sophisticated theories and conduct more precise observations, we will gradually converge on truth. It may be a truth that surpasses our current imagination. It may reveal that we are embedded in greater structures than we currently suspect. It may show that reality is far more complex, far more beautiful, far more inexplicable than we have yet conceived. And if it does, that will be wonderful. Not wonderful merely in the sense of making us happy, though it might, but wonderful in the deepest sense, full of wonder, capable of inspiring awe, a reminder that the universe exceeds our comprehension, that the quest to understand is endless, that consciousness itself is one of the most remarkable features of reality. We are small. We are brief. We are insignificant by the measure of cosmic distance and time. We exist for a few decades out of billions of years of cosmic history. We occupy a tiny rocky world orbiting an ordinary star and a galaxy among trillions. Yet we are here. We are aware. We are asking profound questions about our place in the cosmos. And in that questioning, in that drive to understand, lies something magnificent and transcendent. The universe might be inside something much bigger. And if it is, then we are inside something much bigger as well. The boundaries of our universe are perhaps not the boundaries of reality. The laws we have discovered govern our cosmos, but perhaps they are laws that apply throughout a vaster realm. Yet even if this proves false, Even if our universe stands alone, the investigation continues. The quest for knowledge goes on. We look upward, outward, inward into the mathematics of reality, and we ask our questions. We gather data. We refine our theories. We approach truth with humility and courage, with wonder and determination. This is the future of cosmology, not a final answer, but an endless exploration. Not a destination, but a journey. Not a moment of complete understanding, but an eternal process of deepening comprehension punctuated by moments of profound wonder and revelation. We are voyagers in a cosmos of almost incomprehensible magnitude. We have barely begun our journey. The universe, and whatever lies beyond it, awaits our investigation. And in that investigation, in that quest for truth, we become most fully human. We realize our potential as conscious beings capable of understanding the cosmos that created us. Epilogue. The horizon calls. This is our cosmic moment. We stand at a threshold, peering beyond the boundaries of the observable universe, asking if there is anything beyond. The answer may surprise us. It may humble us further. It may reveal wonders we have not yet imagined. But the question itself, the asking, the seeking, the striving to understand, this is what makes consciousness possible. This is what makes us alive. The universe is vast. It stretches 93 billion light years across, or more, if we count commoving distances accounting for expansion. It may be vastly larger than we yet realize, vastly more complex, containing multitudes we have not yet imagined. And within that vastness, we exist, small but aware, brief but curious, insignificant by measure, but capable of contemplating infinity. This is enough. This is everything. This is the eternal gift of consciousness in a cosmos of wonder. In the end, we are bound to the cosmos not merely through the matter that makes up our bodies, but through our capacity to understand it. We are the universe becoming conscious of itself. And in that consciousness lies the deepest truth about existence. We matter, not because we are large or central, but because we are aware. We are the cosmos knowing itself, and that knowledge is the highest form of meaning available to us. Part 26. The detection methods and observational signatures. Understanding precisely how scientists would detect evidence of other universes requires careful consideration of the physical mechanisms through which such universes might manifest their presence. If our bubble universe is adjacent to other bubble universes, the interaction would occur at a boundary region of extraordinary physical complexity, where the laws of nature themselves might behave in unexpected ways. The boundary between two universes would not be a simple wall or membrane in the conventional sense, but rather a region where the properties of space-time transition from the characteristics of one universe to those of the other. At such a boundary, we would expect several observable effects that might be detectable through careful astronomical observation and data analysis. If the neighboring universe has a slightly different vacuum energy density, a different dark energy density, then the gravitational field at the boundary would be noticeably distorted. The curvature of space-time would be different on the two sides of the boundary. Light traveling from our universe into this boundary region would experience gravitational lensing, a bending of its path due to the curved space-time geometry. More remarkably, if the temperature of the early universe differed between the two bubble universes, we would observe a corresponding difference in the temperature of the cosmic microwave background radiation in the direction of the boundary. Radiation from the other universe, if it could somehow reach us across the boundary, would carry crucial information about the universe's thermal properties, its composition, and its history. Recent sophisticated analyses of the Planck satellite data have claimed to identify regions of the CMB that show patterns consistent with such collisions. One research group, led by Stephen Feeney of Princeton University, claimed to find evidence for what they called Hawking points, spherical patterns in the CMB that would be expected as supermassive black holes from a neighboring universe had impacted our universe's boundary, releasing enormous amounts of Hawking radiation as they crossed the boundary and evaporated into nothingness. The idea is elegant and scientifically sound. In the neighboring universe, supermassive black holes would exist at the centers of galaxies, just as they do in ours. If a neighboring universe collided with ours, or if their boundaries overlapped in some region of space-time, some of these black holes might impinge on our universe's boundary. As they cross through the boundary, they would decay and release energy in the form of Hawking radiation. This radiation would leave an imprint on the CMB that might be detectable through careful analysis. Part 27. The cosmological simulations and computer modeling. As theoretical understanding has advanced substantially, cosmologists have developed increasingly sophisticated computer models to simulate the evolution of the universe from its earliest moments to the present day. These simulations start with initial conditions matching what we observe in the early universe, small density fluctuations derived from quantum mechanics, and allow gravity to act to evolve the system forward in time according to Einstein's equations. The results of these simulations are compared meticulously to observations from telescopes and satellites. If the simulated universe produces a distribution of galaxies and large-scale structures similar to what we observe in the actual cosmos, that suggests our theoretical understanding is correct. If there are significant discrepancies, it suggests we are missing something important about how the universe actually works. Remarkably, some of the most advanced simulations have produced results that are subtly but significantly different from what simple inflation models would predict. The simulations show unexpected alignments in the distribution of structures, correlations that extend to larger scales than expected, and other subtle anomalies that prompt researchers to reconsider fundamental assumptions. Some researchers have speculated that these discrepancies might be evidence that the universe has finite extent and non-trivial topology, as we discussed earlier. If the universe is truly a compact, finite space with particular topological properties, then the large-scale structure that forms would necessarily reflect those properties in its patterns and distributions. Part 28. The role of string theory and M-theory. String theory and its extension, M-theory, play a crucial and increasingly important role in the theoretical framework supporting the multiverse hypothesis and our understanding of fundamental physics. In string theory, the fundamental objects in nature are not point particles, but one-dimensional strings vibrating in a higher dimensional space, each with its own characteristic frequencies and modes of vibration. The properties of the vibrating string, its vibrational modes, the way it wraps around extra dimensions, the interactions it has with other strings, determine what we observe as particles and forces in our universe. Different vibrational modes correspond to different particles. The graviton, the particle that mediates gravitational force, emerges naturally as the massless state of a closed string moving through space-time. String theory requires the existence of extra spatial dimensions, 10 spatial dimensions plus time, or 11 dimensions in the most advanced version called M-theory. These extra dimensions cannot be observed directly in our current experiments because they are compactified at incredibly tiny scales, on the order of the Planck length, 10 to the power of negative 35 meters, far below anything we can probe with current technology. The cosmic landscape of string theory, the vast space of possible configurations of extra dimensions and field values, contains roughly 10 to the power of 500 possible vacuum states, each corresponding to a different possible universe with profoundly different physical properties. Most of these universes would be sterile, containing no galaxies or stars or any possibility of observers. But a tiny fraction would have properties compatible with conscious observers like ourselves. Part 29. Alternative explanations and scientific skepticism. To present a balanced and intellectually honest perspective, we must seriously and carefully consider alternative explanations for the anomalies we observe in cosmological data. Not all cosmologists in the field accept the multiverse interpretation of the CMB anomalies and other observed features, and their skepticism is often well-founded and scientifically justified. Some researchers propose that the anomalies might be explained by modifications to Einstein's theory of gravity itself. If gravity behaves differently on cosmic scales than Einstein's equations predict, perhaps following different mathematical laws at very large distances, it might produce the patterns we observe without requiring a multiverse. These modified gravity theories propose fundamental changes to gravitational physics at the largest scales of the universe. Other researchers propose that the anomalies might result from more sophisticated models of cosmic structure formation, models that account for the complex and still not fully understood dynamics of dark matter and dark energy. If the dark energy is not truly uniform throughout space, but varies slightly from place to place, or if the dark matter has more complex properties than simple models assume, it might produce the observed patterns in the data. There is also the possibility of observational bias and systematic errors in how we process and analyze data. Perhaps the anomalies are artifacts of how we process the data from satellites and ground-based telescopes. If scientists made choices in their analysis that unconsciously or consciously favor finding certain patterns, this could lead to false discoveries that seem significant but are actually statistical flukes. The multiverse explanation is compelling because it provides a unified framework that naturally explains multiple separate observations and phenomena: the fine-tuning problem, the CMB anomalies, the large-scale structure, and other puzzles. Yet precisely because it is so comprehensive, it is difficult to refute definitively with any single observation. Part 30. The intersection of science and philosophy. The questions we have explored in this lengthy essay exist at the boundary between empirical science and philosophical inquiry. They ask not just how the universe works mechanically, but whether there might be multiple universes, whether reality is truly three-dimensional or is a holographic projection of a lower-dimensional surface, whether the physical constants might be accidents or cosmic necessities. These are questions that science can inform and constrain, but cannot definitively answer through empirical observation alone. Science is supremely effective at answering questions of the form, "How does this work?" and "What will happen next?" But questions of ultimate origin, "Why is there something rather than nothing?" transcend the proper scope of empirical science. Philosophy has always played a role in science, often in ways that are not explicitly acknowledged or discussed. When scientists choose to adopt the cosmological principle, the assumption that the universe looks approximately the same in all directions, they are making a philosophical choice grounded in principles of simplicity and a rejection of human importance. The multiverse framework represents an extension of this philosophical reasoning to new domains. It proposes principles that seem to emerge from mathematical analysis of quantum mechanics and general relativity, but whose truth value cannot be established through direct experiment or observation. In this sense, the investigation of the multiverse represents science at its most philosophically sophisticated, bringing together rigorous mathematics, careful observation, and deep philosophical reasoning to probe the deepest questions about the nature of existence. Part 31. Human significance and meaning in a vast cosmos. An important philosophical point emerges from our contemplation of vast cosmic scales and the possibility of a multiverse. The fundamental question of what makes anything significant or meaningful in an existence that might be cosmic foam containing infinities. If our universe is merely a bubble among infinitely many others, does that make our existence meaningless? Does the vastness of the multiverse diminish the importance of individual human lives and human consciousness? A philosophical argument can be made in exactly the opposite direction. The fact that consciousness has emerged at all, that the universe has become aware of itself through conscious beings capable of asking profound questions, is remarkable and deeply significant, regardless of scale or cosmic context. The intricate complexity of a single human brain, with its 86 billion neurons and trillions of synaptic connections forming an almost incomprehensibly intricate network, rivals in complexity the structure of galaxies and cosmic filaments stretching across billions of light years. The meaning of our lives does not depend on how large or central we are in the cosmic order. A single atom within a human body is infinitesimal compared to the body, yet it plays a crucial role in the functioning of that body. Similarly, human consciousness, though tiny in cosmic terms, may play a crucial role in the functioning of the broader universe. The pursuit of knowledge itself has intrinsic value. It is one of the highest expressions of human consciousness, one of the ways in which we actualize our potential as conscious beings capable of comprehending reality and our place within it. Part 32. The Ultimate Mystery and Final Wisdom. After all this extensive exploration, after considering the evidence for and against a larger containing structure, after examining the theories and the observations in meticulous detail, we must acknowledge a deeper truth. There are mysteries that may forever exceed our comprehension, mysteries that may lie fundamentally beyond the reach of human understanding. Even if we confirm that our universe is embedded within a multiverse, that only pushes the ultimate question back one level of explanation. If the multiverse itself is infinite and eternal, why does it exist? Why is there a multiverse rather than absolute nothingness? If the multiverse itself is finite and contained within something still larger, we face the same question at a higher level. We can construct an infinite regress of containing structures, but eventually we must confront the ultimate question: what lies at the foundation of existence? What is the ground of being? Some physicists have speculated that this ultimate question might not have an answer, at least not an answer that is comprehensible to minds like ours. The universe might be fundamentally self-explaining. Existence might be necessary rather than contingent, following inevitably from some deep principle of logic or mathematics. The honest recognition of the limits of human knowledge is not a weakness, but a strength. It reflects intellectual humility and honesty. We do not claim to understand everything. We do not claim that science can answer all questions. But we continue to investigate, to observe, to think, and to question, pushing the boundaries of human knowledge ever outward. This is the human condition. We are conscious beings capable of understanding a significant portion of reality, yet we remain forever bounded by the limits of our minds and the constraints of our position within the universe. We are simultaneously insignificant and magnificent, tiny yet conscious, mortal yet capable of grasping infinity. And it is in this paradox, in this combination of insignificance and power, of limitation and transcendence, that human existence finds its deepest meaning and its eternal significance. The universe may be vastly larger than we can imagine, containing multitudes of other universes, other worlds, other observers. And yet, here we are, conscious creatures made of star stuff, capable of contemplating the infinite. This is not a curse or a tragedy. This is the most remarkable gift existence can offer: awareness of itself through our consciousness, knowledge flowing through our minds, wonder at the majesty of reality. We may never know with absolute certainty whether our universe is embedded within something larger. But the quest for that knowledge, the striving to understand our place in the cosmos, is itself profoundly meaningful. In that quest, we become fully human. In that search for truth, we actualize our deepest potential. And that is enough. That is everything. The horizon calls. The cosmos waits. And we, conscious observers in an incomprehensibly vast reality, continue to look outward, asking our eternal questions, seeking to understand the infinite structure of existence. Part 33. The evolution of multiverse theory and its implications. The concept of multiple universes has evolved dramatically over the past few decades, transforming from a purely philosophical speculation into a serious scientific hypothesis grounded in fundamental physics. The evolution of this idea deserves careful examination, as it shows how scientific understanding develops and changes as new observations become available and new theoretical insights emerge. In the 1980s, when Alan Guth first proposed inflationary cosmology, the concept of the multiverse was barely mentioned in serious scientific circles. Inflation was presented as a mechanism to solve specific problems in cosmology, the flatness problem, the horizon problem, and others. It was a solution to observational puzzles, not a pathway to multiple universes. But as Andrea Linde and others developed the theory further, they realized something remarkable. Eternal inflation naturally produces a multiverse. This was not something they were trying to achieve. Rather, it was an almost inevitable consequence of taking the mathematics of inflation seriously. If you allow inflation to proceed according to quantum mechanical principles, you get eternal inflation and a multiverse of bubble universes. This realization was initially controversial. Many physicists found the idea of a multiverse philosophically problematic. How could something that cannot be observed, cannot be measured, cannot be directly tested be part of physics? Isn't physics supposed to deal with the observable and measurable? Yet over time, the multiverse idea gained acceptance, not because it became more philosophical, but because it became more testable. Researchers realized that even if we cannot directly observe other universes, we might see their effects on our own universe. We might detect signatures of universe collisions in the CMB. We might find patterns in large-scale structure that could only be explained by the finite size and geometry of our universe embedded within a larger multiverse. This transformed the multiverse from pure speculation into a scientific hypothesis, something with predictions that could be tested against data. The shift from philosophy to testable physics happened gradually, but it happened nonetheless. Part 34. The measurement problem and observer selection. One of the most profound implications of the multiverse hypothesis concerns the nature of probability and measurement in physics. In the standard interpretation of quantum mechanics, when we measure a system, we get one of several possible outcomes, each with a certain probability. But where do these probabilities come from? What determines them? In the multiverse picture, all possible outcomes actually occur. Each quantum event, instead of resulting in one outcome with a certain probability, results in all possible outcomes occurring in different branches of the multiverse. There is no need to talk about probability at all. Everything that can happen does happen, somewhere in the multiverse. This is the many-worlds interpretation of quantum mechanics, originally proposed by Hugh Everett in 1957, but largely ignored until the multiverse hypothesis became more mainstream. In this interpretation, every quantum measurement splits the universe into multiple branches, one for each possible outcome. This has profound implications for how we think about probability and meaning. If all possible outcomes occur somewhere in the multiverse, then in some sense, we are guaranteed to find ourselves in a universe where we exist, and of conscious experiences. We cannot find ourselves in a universe where we do not exist, because non-existing entities cannot have experiences or observations. This is the anthropic principle again, but now understood not as a philosophical principle, but as a straightforward consequence of the multiverse structure combined with the fact that we exist and are conscious. We observe our universe to have the properties it does because we could not observe any other kind of universe. Part 35. Implications for the future of cosmology. The future of cosmology will likely be shaped by attempts to resolve the questions we have discussed. Will the multiverse hypothesis prove to be correct? Will we find evidence of other universes? Or will new observational data and theoretical insights suggest alternative explanations for the anomalies we have observed? The key to progress will be improved observations of the CMB, large-scale structure, and other cosmic phenomena. The upcoming generation of telescopes and satellites will provide data far more precise than anything we have available today. These observations will either confirm the predictions of multiverse theory or suggest that alternative explanations are more plausible. Simultaneously, theoretical physicists will continue to develop new frameworks for understanding fundamental physics. The quest for a unified theory combining quantum mechanics and gravity, a theory of quantum gravity, continues actively. Such a theory might reveal surprising new insights into the structure of the multiverse, if it exists. There is also the possibility of entirely new discoveries we have not yet anticipated. Throughout the history of science, some of the most important advances have come from unexpected directions. A new observation might reveal something about the cosmos that nobody had predicted, forcing us to revise our understanding entirely. This uncertainty is part of what makes science exciting and important. Part 36. The grandeur and humility of scientific understanding. As we conclude this long exploration of the possibility that our universe exists within something much larger, it is worth reflecting on what this whole investigation reveals about science itself and about the human endeavor to understand reality. Science is both grand and humble. It is grand in its scope. We have developed frameworks allowing us to understand the structure of atoms, the birth and death of stars, the evolution of galaxies over billions of years, and the fundamental laws governing all of reality. Yet science is also humble in its acknowledgement of limitations. We do not claim to have all the answers. We do not claim that our theories are final or complete. We recognize that our understanding will likely be superseded by future discoveries and deeper insights. This combination of grandeur and humility is what makes science powerful and reliable. We are bold enough to ask profound questions about the nature of existence itself. Yet we are humble enough to acknowledge when we do not have answers, to admit when our understanding is incomplete, to remain open to evidence that might contradict our current beliefs. The multiverse hypothesis exemplifies this combination. It is a grand idea, the notion that our universe is one among infinitely many, each with different properties and histories. Yet it is grounded in humble recognition of what we do not know, what we cannot directly observe, and the limits of our current understanding. The investigation of whether our universe is embedded within something larger is an ongoing process. We have not reached a final answer. Likely, we never will. But the process of investigation itself, the asking of questions, the seeking of evidence, the refining of theories, is what moves human knowledge forward and what makes us fully human. This is the spirit of science at its best. Bold questioning combined with intellectual humility, grand vision combined with careful attention to evidence, philosophical depth combined with mathematical precision. In this spirit, we continue to investigate the cosmos, to probe its secrets, and to seek understanding of our place within its vast structure. Part 37. The Cosmic Perspective and Personal Meaning. Standing back and surveying all that we have discussed, we must consider what it all means for us as human beings. How should we respond to the possibility that our universe might be one among infinitely many? How should we think about our own significance in such a vast structure? Throughout history, humans have grappled with the question of meaning and significance. What makes our lives important? What makes anything meaningful in a universe so vast and old that our individual existences are like mayflies lasting seconds in the context of cosmic time? The traditional religious answers to this question have centered on the idea that human beings hold a special place in creation, that we are made in the image of God, that our consciousness and free will give us a unique significance. These answers provided comfort and meaning for billions of people across millennia. Modern science has gradually revealed that we are not special in the ways our ancestors thought. We are not at the center of the universe. We are not the purpose for which creation was made. We are not placed above nature, but a part of it, subject to the same physical laws that govern stars and atoms. Yet this revelation, rather than diminishing human significance, can be understood as revealing a deeper and more authentic basis for meaning. We find significance not in being central or special, but in being conscious, in having the remarkable capacity to know and understand. We are the universe examining itself, the cosmos becoming aware of its own structure and history. Carl Sagan and other thoughtful scientists and philosophers have emphasized this point. The fact that we can contemplate the cosmos, develop mathematical theories describing its behavior, discover the laws governing its operation, this is remarkable and deeply significant. It is a form of dignity that does not depend on cosmic centrality or special creation, but arises from the intrinsic value of consciousness and understanding. In the context of a possible multiverse, this perspective becomes even more profound. If there are indeed infinitely many universes, most of them devoid of conscious observers, then the emergence of consciousness in our universe becomes even more remarkable. The probability that consciousness would emerge anywhere in the multiverse might be infinitesimal, yet it has happened here, in this universe, in this cosmic bubble floating among others. The fact that we exist, that we are conscious, that we could understand something of the cosmos, this is extraordinary and meaningful regardless of how many other universes might exist beyond our reach. Part 38. The beauty of cosmic structure. One aspect of contemplating the cosmos that we have not emphasized enough is the sheer beauty of its structure. Beyond the mathematical elegance of the equations describing physical laws, beyond the intellectual satisfaction of understanding how things work, there is a profound aesthetic dimension to cosmic reality. The structure of a spiral galaxy with its rotating disk of stars and dust is aesthetically magnificent. The intricate patterns of cosmic web, the filaments of galaxies surrounding vast voids, have a strange and otherworldly beauty. The supernova explosions that briefly outshine entire galaxies are among the most beautiful and violent phenomena in nature. The cosmic microwave background, that ancient light from 380,000 years after the Big Bang, has been mapped in exquisite detail, revealing patterns and structures that are genuinely beautiful. The tiny temperature fluctuations, when visualized, appear like a landscape of cosmic geography, mountains and valleys in the fabric of space-time itself. Even the abstract mathematical structures that describe physical laws have a beauty that physicists and mathematicians have long recognized. The equations of general relativity, the symmetries of quantum field theory, the geometries emerging from string theory, all display a kind of aesthetic elegance that suggests something deep about the relationship between mathematics and physical reality. This aesthetic dimension of scientific understanding is often overlooked in discussions of science and evidence. We tend to emphasize the empirical and the practical, Does it work? Can we measure it? Does it predict new phenomena? These are important questions, but they are not the whole story. Science also satisfies a deep human aesthetic sense. The desire to find beauty, pattern, and elegance in nature is as fundamental to the scientific enterprise as the desire to build bridges or cure diseases. A physical law is more satisfying when it is elegant and beautiful as well as accurate. This aesthetic dimension suggests that there is something right about the multiverse hypothesis, not just because of its empirical predictions and logical consistency, but because it has a certain elegant and beautiful quality. It explains multiple puzzles with a single elegant framework. It shows how the apparent fine-tuning of our universe follows naturally from an ensemble of universes with different properties. Part 39. The role of imagination in scientific discovery. Throughout this essay, we have discussed observations, data, mathematical theories, and empirical evidence. But we should not forget the crucial role that imagination plays in scientific discovery. Many of the greatest scientific advances have come from imaginative leaps, from people able to visualize structures and possibilities that had never been directly observed or measured. Darwin imagined the tree of life, showing how all species might be related through common descent. Maxwell imagined electromagnetic waves traveling through space, years before they were detected experimentally. Einstein imagined what it would be like to ride on a beam of light, and this imaginative exercise led to his theory of special relativity. The multiverse hypothesis similarly emerges partly from mathematical analysis, but partly from imaginative thinking about cosmic structure. Physicists had to imagine what would happen if universes could collide, what signatures they would leave, what patterns would emerge. This imaginative thinking, combined with careful mathematical analysis and comparison with observational data, is what drives forward the investigation of the multiverse. Imagination is not the opposite of scientific rigor, but a complement to it. A purely mechanical application of mathematical techniques without imaginative insight would never generate new ideas or new directions for investigation. But imagination without the constraints of mathematical rigor and empirical testing would lead only to unfounded speculation. The productive use of imagination in science is what moves the field forward. It is what allows scientists to conceive of new possibilities, to ask questions nobody has asked before, to imagine structures and phenomena that nobody has yet observed. The investigation of the multiverse represents imagination in service of understanding, bold questioning grounded in mathematics and constrained by evidence, imaginative thinking tempered by empirical observation and theoretical rigor. Part 40. Concluding thoughts on the cosmic mystery. We have reached the conclusion of this extensive exploration of the possibility that our universe exists within something much larger. We have examined the evidence, considered the theories, explored the philosophical implications, and contemplated what this all means for our understanding of ourselves and our place in reality. The honest truth is that we do not yet know whether our universe is truly embedded within a larger multiverse or whether it stands alone. The evidence is suggestive, but not conclusive. The theories are mathematically elegant, but largely untestable. The anomalies and observational data could be interpreted in multiple ways. Yet, this uncertainty is not a weakness or a failure of science. Rather, it is a reflection of where we stand at this moment in the history of human understanding. We have pushed our knowledge far beyond what our ancestors imagined possible. We have developed theories describing the behavior of the universe from its earliest moments to the present, across distances from subatomic scales to billions of light years. We have achieved a level of understanding that would have seemed like magic to previous generations. And yet, fundamental mysteries remain. The structure of the multiverse, if it exists, remains beyond our direct observation. The ultimate nature of reality, what lies at the foundation of existence, remains a question that transcends the current scope of science. But this does not mean we should give up the investigation. Rather, it means we should continue with renewed determination, developing new instruments to observe the cosmos with greater precision, developing new theories to explain what we observe, and continuing to ask profound questions about the nature of existence. The universe, or the multiverse, or whatever larger structure might contain it, is far more vast, far more complex, far more beautiful than our ancestors imagined. And we, creatures of star stuff capable of contemplating infinity, are privileged to be part of this cosmic existence, to understand something of its structure, and to continue the eternal human quest for knowledge and understanding. The horizon of the unknown calls to us still. And as conscious observers in this incomprehensibly vast reality, we continue to listen to that call to investigate, to question, and to seek understanding. This is what makes us human. This is what gives our existence meaning and purpose. And this is enough. This is everything. Epilogue, the universe's greatest questions. As we face the closing thoughts of this lengthy meditation on cosmic structure and the possibility of universes within universes, it is fitting to consider what the biggest questions still before us truly are. Perhaps the deepest question is not, is our universe embedded in something larger? But rather, what does it mean that there is anything at all? This question precedes all others. It asks about the very ground of existence. It asks why being is possible at all. Physics, as currently understood, cannot fully answer this question. Physics can describe how the universe came into being, how it evolved, what laws govern its behavior. But it cannot ultimately explain why these laws exist, why the physical constants have their particular values, why there is something rather than nothing. This ultimate question might be forever beyond the reach of physics. It might require philosophical or spiritual insights beyond what empirical science can provide. Or it might be that the question itself is flawed, that there is no reason for existence, that being simply is, without need for external justification or causation. Many physicists have suggested that the laws of physics might be necessary truths, that given the basic principle that something exists and evolves, the specific laws we observe might follow inevitably. If this is true, then the universe we observe, and potentially the multiverse containing it, might be the only possible structure consistent with logical necessity. This is speculative, but it is the kind of speculation that theoretical physics engages in at its deepest levels. We are trying to understand not just how the universe works, but why it works the way it does, and whether any other way of working is logically possible. The role of consciousness in the cosmos. Another profound question that emerges from our investigation is the role of consciousness in the cosmos. Are we merely accidental observers, consciousness arising by chance in one particular universe? Or is consciousness more fundamental to cosmic structure than we realize? Some physicists and philosophers have suggested that consciousness might be more deeply woven into the fabric of reality than mainstream science acknowledges. The quantum measurement problem, the fact that the act of observation seems to affect the outcome of quantum measurements, has led some to speculate that consciousness might play a role in determining physical outcomes. Most mainstream physicists dismiss such ideas as unscientific speculation. They argue that the measurement problem can be resolved without invoking consciousness, through careful analysis of the quantum mechanical formalism and the nature of decoherence and wave function collapse. Yet the question persists. In a universe described by probability amplitudes and wave functions, in a universe where the act of measurement affects the measured quantity, is there a role for consciousness? Is the emergence of consciousness in the universe a cosmic accident, or is it somehow built into the fundamental structure of reality? We do not have a definitive answer to these questions. But the fact that consciousness has emerged, that the universe has become aware of itself, is remarkable regardless of whether consciousness played any fundamental role in cosmic structure or emerged entirely by accident from physical processes. The search for extraterrestrial intelligence. One question raised by the possibility of a multiverse is whether other universes might contain extraterrestrial intelligence. In our own universe, we are alone as far as we currently know. No confirmed contact with intelligent extraterrestrial life has been made, despite decades of searching. But if the multiverse is real, and if many bubble universes exist with different physical properties, then some of them might be far more conducive to the emergence of intelligent life than our own. Some might have physical constants far better suited to the formation of stars, planets, and biological systems. Some might be far older than our universe, having had billions of years more to allow intelligence to emerge and flourish. In this broader context, our apparent solitude becomes less surprising. In any given universe, the emergence of intelligence is likely rare. Intelligent species will be separated not just by cosmic distances within their universe, but by the fundamental barriers separating one universe from another. Contact between intelligences in different bubble universes would be essentially impossible due to the expansion of space separating the universes. Yet within our own universe, the search for extraterrestrial intelligence continues. Radio signals are monitored for signs of technological civilizations. The chemistry of potentially life-bearing exoplanets is being analyzed. The possibility of discovering we are not alone remains one of the most profound possibilities for future discovery. The ultimate scope and scale of reality. Having contemplated universes containing trillions of galaxies, having considered the possibility of multiverses containing infinitely many universes, each with different properties, we must ask, is there any limit to the scope and scale of reality? In the mathematical framework of eternal inflation and string theory, the multiverse is infinite. Infinitely many bubble universes, each infinitely large, containing infinitely many atoms and particles. An infinite structure, containing infinite complexity, existing eternally into the past and the future. To attempt to comprehend infinity is to push against the boundaries of human thought itself. Our minds evolved to navigate a world of finite scales, trees with finite numbers of leaves, herds with finite numbers of animals, territories with finite dimensions. We have extended our thinking through mathematics and abstraction to encompass vastly larger scales. Yet infinity remains, in some sense, beyond full human comprehension. Yet this infinity is not meaningless. Each bubble universe, each galaxy, each atom has a particular structure and history. The infinite complexity that emerges from the infinite ensemble of universes is not featureless or undifferentiated. Rather, it is a rich structure of tremendous complexity, allowing for the emergence of complexity, beauty, and consciousness. Our position within this infinite structure is infinitesimal yet conscious. We are specks of awareness within an infinite cosmos. And that awareness itself, that consciousness capable of pondering infinity, is what gives meaning and significance to our existence. Final words on the universe within. The question with which we began, is our universe inside something much bigger, remains open. Evidence accumulates. New observations become available. Our theoretical understanding deepens and evolves. Yet the definitive answer remains beyond our grasp. But perhaps the answer itself is less important than the process of seeking it. In asking this question, in gathering evidence, in developing theories to explain what we observe, we are engaging in the most characteristically human of all activities, the pursuit of understanding. We are conscious beings in a vast cosmos. We are made of matter forged in stellar furnaces. We are products of billions of years of cosmic and biological evolution. And we have the remarkable capacity to understand something of the cosmos that created us. That is not insignificant. That is not meaningless. That is, in fact, the foundation of all meaning, the conscious awareness of reality, the drive to understand, the ability to question and seek truth. Whether our universe is one among many, whether it is embedded in structures beyond our comprehension, whether multiple layers of reality exist above and beyond what we can observe, all of these questions point to something fundamental about existence, that it is mysterious, deep, and worthy of investigation. We continue to look upward and outward. We continue to question and observe and theorize. We continue the eternal quest to understand our place in the cosmos. And in that continued searching, we fulfill our highest purpose as conscious beings capable of comprehending the universe in which we exist. The horizon of mystery remains, calling us ever forward. And we, small but aware, mortal yet conscious, continue to answer that call. This is our cosmic destiny, to know, to understand, to comprehend ourselves and the reality that contains us. It is a privilege and a responsibility that we carry forward as we continue our investigation into the deepest mysteries of existence.